This video is looking at the fundamental theorem of calculus part 2, and it's a very important theorem in that it makes the big connection between derivatives and integrals, but we'll get to that in just a few minutes. We're going to start out with a warm-up, and hopefully you have completed the warm-up on your own without using a calculator, and let's see what's going on here. Because Jeb, of course a former student, doesn't show all of his work in calculus, he can't get into college, and he decides to take a job at the circus as the human cannonball. He's fired from a cannon with a velocity of negative 32t plus 150 feet per second. This is important, and this is part of the reason that we're not going to need our calculator, because the problem tells us he reaches his maximum height at a time of t equal to 75/16 of a second. That's going to be something we're eventually going to use. Question A. What is Jeb's initial velocity? Well, I want to know his velocity at time 0, so I get negative 32 times 0 plus 150, which is 150 feet per second. Determine his average velocity. Keyword, find the average of velocity. So they want me to find 1 over b minus a. This is what we just did in our homework. From a to b of v of t dt, the average of velocity. In other words, I have to go back to position because average velocity is change in position over change in time. So we get 1 over 4 minus 0 from 0 to 4 of negative 32 t squared plus 150 dt, which is 1/4 of negative 32t negative 16 t squared plus 150t evaluated from 0 to 4, which is, I'm going to go down here, 1/4 of 344. I'm not showing the calculations. You can do the calculations by hand. And 344 divided by 4 is 86 feet per second. That is his average velocity over that time interval. Obviously, he was going faster to begin with and slower at the end, and so this is his average. Question C, letter C. At what time? Alright, so this is mean value theorem without saying mean value theorem. At what time does he reach his average velocity? In other words, when is his average rate of change equal to his instant rate of change? So I'm going to take his average rate of change, which we just found to be 86. I'm going to set it equal to his instant rate of change, which is negative 32t plus 150. I'm going to solve that equation by subtracting 150 from both sides. And 86 minus 150 is negative 64, equal to negative 32t. Divide both sides by negative 32, and t is equal to 2 seconds. So this is the time at which he was actually traveling at an instant, 86 feet per second. Okay, so that's your connection, average value, mean value theorem. Letter D, write an integral that represents Jeb's displacement from 0 to 6. Well, that's very easy. That would be from 0 to 6 of v of t dt. Let me make sure that they did name that v of t, so I can use, I can use that name as long as they name it. And then for letter E, write an integral that represents total distance. Now this is where you would think, oh, I want a calculator. I need to know when the velocity is positive and when the velocity is negative. However, if you put the puzzle together, you already know that your position function, alright, so you have your velocity function right here. You already know that your position function is going to be negative 16t squared plus 150t plus c. And it doesn't matter what c is. The key is it's a parabola that opens downward. So, and we already know from this part right here that the maximum height, this guy right here, occurs at 75/16. That's the time, not the height. So we know that velocity, since the slopes on this side are positive and the slopes on this side are negative, that to the left of 75/16 we have positive velocity, and to the right of 75/16 we have negative velocity, and we need to force it to be positive to get total distance. So we're going to have the integral from 0 to 75/16 of v of t. Remember, that area was positive, and we need to force the next region of area to be positive, so we're going to negate or minus 75/16 to 6 of the velocity dt, and that would represent the total distance traveled over that period of time. And you can go back and look at and think about that more if you need to. All right, let's go on to the some of the homework questions. I'm not sure. Let's take a look at number 59. Every single one of these was average value. So in number 59, setting it up for you would be 1 over b minus a. So that would be 1 minus negative 1, which would be 2. The integral from negative 1 to 1 of 2e to the x dx, which would be 1/2 of, when you take the derivative, or excuse me, when you find the antiderivative of e to the x, you get e to the x. From negative 1 to 1, I'm going to go ahead and divide out those 2's, and I'll have e to the x from negative 1 to 1, which is e to the first minus 1 over e. What happened there? That was e to the negative 1, which would go to the denominator and become 1 over e. I'm trying to look and see if any of these are really, really hard. Oh, now it does say it also says do the mean value theorem. So it's wanting to know when the average rate of change is equal to the instant rate of change. So that's a little bit more challenging. So my instant rate of change is 2e to the x, and my average rate of change is e minus 1 over e. So I got to do a little work here. 2e to the x, I'm going to get a common denominator on the right hand side, and I'll get e, and that'll be e squared minus 1. I'm solving for x, so let's see, what do I want to do with this? Trying to think of the easiest way to solve this. Let's do e to the x. I'm going to divide by 2 is equal to e squared minus 1 over 2e. I'll take the ln of both sides. That'll give me x on the left hand side. In cleaning that up, that would be the same thing as, you know what, just leave it for now. I mean, we could do a little bit of cleaning, but for now, just leave it. If you have other questions on the average value theorem, bottom line, it's 1 over b minus a from a to b of f of x dx. It's really just a formula. So if you have other questions that you're just not quite sure about, come and see me, and I'll be glad to help you with those. 63 is an oldie but a goldie. You have a velocity graph, and you're estimating the distance a car travels in 8 seconds. So if I were doing this problem, I would draw my line. It almost looks like a triangle. And that might be a little underestimation. I mean, you could count the blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, almost 12, 13, 14. You could count the blocks and figure out, in this case, that one block is 2 units by 15 units. So you could count your blocks and multiply by 30. You could use geometry. You could use Riemann. Lots of ways you could estimate that total distance traveled. All right, let's get to, let's look at this one. We're going to use the graph. The shaded region A has an area of 1.5, so I'm going to put it down here, and I'm going to put a negative 1.5. And 0 to 6 has an area of 3.5, so all of this together, all of that area is 3.5. And so if this is negative 1.5 and this is 3.5, then this would be an area of 2. the area of B would be 2. And then you start answering the questions. The absolute value is going to flip all the area to be positive. The negative 2 we can pull on the outside using our properties. 0 to 2, 0 to 6, 0 to 2. Number 71, I'm going to rewrite that as 2. No, I'm not. 0 to 6 of 2. There's your rectangle coming back again, plus 0 to 6 of f of x dx. And remember, this is a rectangle that is 6 units by 2, and 6 times 2 is 12. And then you would get your area from the graph. The average value of f 1 over b minus a, so it would be 1/6 of the integral from 0 to 6 of f of x dx. So that would be 1/6 of the area from 0 to 6, which we know to be 3, and 1/6 of 3 is 1/2. So that would be the average value of the interval. Okay? Again, please come ask me questions or if you have them. All right, let's get to the lesson. Here we go. Fundamental Theorem of Calculus Part 2. It's going to be kind of a duh thing when you see it, because all it does is it takes me from derivative to integral, integral to derivative. It's that connection between the derivative and the integral. So let's take a look at what we have here. Big f of x is an original function. And big f of x is defined as an integral from 0 to x of cosine of t dt. So question number 1 is to find the derivative of f prime of x. Now, something interesting here. Notice that f of x is defined as the integration of cosine of t from 0 to x. It seems like there's something going on with the variable there. Well, let's see what happens. If we follow the normal process of finding a definite integral, then we would find the antiderivative of cosine of t. Now, the antiderivative of cosine of t, who has a derivative of cosine of t? Sine of t. And remember, check that, the derivative of sine is cosine. Now, since it's a definite integral, we're going to go from 0 to x. When we evaluate that, we're going to get, sine of x, so there's my upper bound, minus the sine of 0, which is the lower bound. Now, keep in mind, I wanted the derivative of this. So I found the antiderivative. So this function right here is f of x. Now, I know that I could find the sine of 0, but that's irrelevant. That's not what really matters. Sine of 0 is a number, and that's what I want you to keep in mind. The sine of 0 is simply a number. Now, in this case, it is 0, but remember that it's a number. All right, so if this is f of x, I want to find the derivative. So the derivative of sine of x is cosine of x, and the derivative of a number, any number, 0 or any number, is 0. So f prime of x is cosine of x. Now that seems like a really, really duh process, and the whole idea was that we have a variable of t here, that when we integrate, it stays a t, and there it is right there, but when we do the definite integral, the x is going to go in place of the t, and that's going to be where that replacement comes in. And so when we take the derivative of that, so notice what really happened is that the derivative of the original function is sitting in here, almost. The derivative of f is cosine, but cosine of what? Well, it's cosine of the new variable. Cosine of the new variable. So in general, if we take the derivative, oops, let me get rid of that. Back up here. If we take the derivative of an integral from a constant a to variable x of a function f of t dt. Okay, so notice we have the same scenario. We're going to find the derivative of an integral. We're going to undo. And that's what it does. An integral and a derivative undo each other. So I should get back to the very beginning. So the derivative that I'm looking for should be right in here, because that's what we integrate. We integrate derivatives. But since this is in terms of t, and if we actually did the integration of this function, the x would end up going in here. The derivative is f, little f, of x. That is the shortcut. In other words, instead of having to actually find the antiderivative and do the definite integration, the shortcut is the t comes out, the dummy variable of a t comes out, and the new variable of the x goes in. And the connection is, this is the connection between derivatives and integrals. And I know that it seems kind of dumb and redundant to say that. I think you already realize that when we're integrating a derivative. All right, well, let's see how that plays out in some other examples. And what I want to convince you of is to do these by the shortcut method. Take a look at problem number 2. We have another function, big f of x, which is an original function. And this time we're going to go from 0 to 2x instead of just plain x. Now we're going to do this the long way, and then we're going to find our shortcut method. So let's see what happens. All right, when I find the antiderivative of f, the antiderivative of cosine of t is sine of t. Notice the dummy variable of t is still there, evaluated from 0 to 2x. And that'll give me the sine of 2x minus the sine of 0, which again is a number. In this case, that number is 0, but it won't always be 0. That is equal to big F of x. But I want the derivative. So if I find the derivative of this function, since this is big F of x, now this is important, the derivative of sine is cosine of the angle multiplied by the derivative of the angle, the chain rule, minus the derivative of a number that is always going to be 0, so I get 2 cosine of 2x. So notice the dummy variable of t was eliminated. I replaced that dummy variable of t with the upper function of 2x because this is just a constant. But then when this function is anything other than x, I have to use the chain rule and multiply by the derivative of the inside because it's a composition function. So what are you trying to say now? I'm trying to say that if you find the derivative of an integral from a constant a to any function f of x, all right, let's change that from f of x. Give me a second here to erase that. All right, so if we go from a to a function, I'm going to call it g of x, and my function that I'm going to integrate, my derivative is f of t. Okay, so again, we are finding the derivative of an integral. They're going to undo each other. So it's going to take me back where I started, except the key to success is, I'll write it down here, f of g of x. So in other words, the t comes out, the dummy variable of t comes out, and the new function goes in place of t. Everywhere there is a t, multiplied by the derivative of the inside function, and that's by the chain rule. And that is the shortcut. Instead of having to find the antiderivative and then evaluate it, we can go straight to the derivative. We can undo that integration. Now, I know this may seem like still kind of duh and maybe a little bit confusing, but let's look at a few examples and hopefully that will clarify any confusion that you have. Problem number 1, find the derivative of the following functions. All right, so let's take a look at what we have here. We have a constant of 5, and we have an upper bound of plane x. So if we follow the Fundamental Theorem of Calculus Part 2, it says we're trying to find the derivative of an integral. In other words, they undo each other. So right here, my answer is sitting in there. So remember, take out the t, put in the new function, and multiply by the derivative of the new function. So again, this is the new function, and this is the derivative of the new function. And since it was just a plain x, then the answer just turns out to be ln of x times 1, which is the ln of x. The t comes out, the new function comes in, and you multiply by the derivative of the new function every time. Let's take a look at the next one. We're starting with 4 ln of x. So now I have something as my upper bound that's not just plain x. I'm trying to find the derivative of an integral. So what's the procedure? Take out the t everywhere that there is a t, put in the new function, and multiply by the derivative of the new function. And the derivative of the ln of x is 1 over x. So I get ln of x squared minus 4 over x. What do I do again? Take out the t, put in the new function, multiply by the derivative of the new function by the chain rule. That is the shortcut. So I don't have to find the antiderivative and evaluate it every time. And it's the same procedure every time you're trying to find the derivative of an integral. Let's take a look at letter C. Now notice this time I'm going from a variable to a constant. Well, we can fix that easily. We can turn the bounds around and have that to be the derivative of the opposite of 5 to x, if we want it to fit our form, e to the t squared dt. What's the procedure? Well, we know our answer is going to be negative, first of all. What's the procedure? Take out the t. So I have e raised to the blank squared. Put in the new function. Well, the new function is x. Multiply by the derivative of the new function, which is 1. Now, in every case, you may be going, what about the 5? What about the 4? What about the 5? Remember, we're technically integrating, and then we're taking the derivative, and the derivative of that constant is going to be 0, and that's why we don't have to worry about it. When we clean this up, we get negative e to the x squared. So what's the procedure? Number 1, take out all t's. Number 2, put in new function. Number 3, multiply by derivative of new function. And what you're doing there is you're applying the chain rule when you're doing your derivative. Finally, number 2, let's see what's going on there. We have an original function defined as an integral. Job number 1 is to find f of 2. Well, f of 2, according to this formula, would be 0 to 2. In other words, I'm just putting in a 2 everywhere I see an x of the square root of 3t squared plus 1 dt. Now, at this point, you do not know how to integrate this function. You will eventually, but you don't right now. So we're just going to, for now, we're just going to leave that as an integral, because we could integrate it on the calculator, and if you have time and you want to do that, that's fine. But that would give me the value of f of 2. B, the derivative evaluated at 2. Well, remember, the derivative of f, if we're going to find the derivative of an integral, remember our process? Take out the t, put in the new function of, in this case, x, and multiply by the derivative of the new function, which in this case is 1. So f prime of x is 3x squared, and we're evaluating that at 2, so we get 3 times 2 squared plus 1. 2 squared is 4, times 3 is 12, plus 1 is 13. And the second derivative at 2, well, over here we have our first derivative, so we have to find the second derivative. By the power rule will be 6x, and 2, evaluate that at 2, and we get 6 times 2, is 12. Very easy. So take a look at these notes, follow them very carefully, and hopefully we're not having a snow day, and this is just something that you're looking at to follow up the lesson. But if it is a snow day, you watch this as many times as you want. Your assignment is page 329, number 85, and 87 to 105 odd. And you can check the solution manual for your answers, and I'll see you next time.